Deep in the vastness of space, beyond the planets we know, there's a whisper of a world we've yet to see. It's been named Planet 9, a shy giant believed to be shaping the movement of distant objects in our solar system. This hidden planet might be the missing piece in the cosmic puzzle. So, how do scientists hunt for something they can't see? And if we eventually find Planet 9, what new mysteries could it help us solve? Join us as we delve into the latest findings supporting the presence of this mysterious celestial body, the missing piece of our solar puzzle. The intriguing quest for Planet 9, a hypothetical world beyond Neptune, is driven by the peculiar paths of distant celestial bodies known as trans-Neptunian objects, TNOs. These include notable entities like Sedna and 2012 VP 113, whose orbits are so stretched and skewed that they defy explanation through the gravitational forces of the solar system's acknowledged planets. The notion of an unseen massive planet in the solar system's farthest reaches provides a compelling solution to this cosmic puzzle. TNOs are a diverse group of icy objects orbiting the Sun at a greater average distance than Neptune, which has an orbital semi-major axis of about 30.1 astronomical units AU. Among these, Sedna and 2012 VP 113 stand out due to their highly eccentric or oval-shaped orbits, which take them to extremely distant points from the Sun at their farthest. Sedna's orbit, for instance, stretches from 76 AU at its closest to the Sun to an astounding 937 AU at its most distant. The case for Planet 9 rests on the gravitational effects it seems to exert on these TNOs. Several of them share similar orbital alignments, hinting at a shared gravitational influence. Statistical analyses bolster the argument that these alignments are unlikely to be coincidental. Instead, they suggest the presence of a perturbing planetary body. This potential planet is estimated to have a mass about 10 times that of Earth and is thought to be located hundreds of times farther from the Sun than Earth. Caltech researchers Konstantin Batygin and Mike Brown have propelled the Planet 9 hypothesis. Through mathematical modeling and computer simulations, they've proposed that this planet could have a mass approximately 10 times that of Earth and orbit about 20 times farther from the Sun on average than Neptune. It's believed that Planet 9 could take between 10,000 and 20,000 years to complete a single orbit around the Sun. The search for Planet 9 has been a winding road of discovery and debate. Initially, the idea emerged from observations that several of the most distant objects in the Kuiper belt shared an obscure orbital feature. This led to the suggestion of a small planet's presence, which was later expanded into the full-blown theory of a ninth planet. Despite the lack of direct observation, the indirect evidence continues to accumulate. New findings from astronomers like Scott Shepard and Chadwick Trujillo have added to the body of work supporting the existence of Planet 9. They've reported that the newly discovered set of distant solar system objects travels in surprising orbits, further hinting at the gravitational pull of a massive planet, decoding Planet 9's secrets. The search for the elusive Planet 9 is a fascinating blend of astrophysical detective work and advanced computational modeling. Researchers have turned to sophisticated computer simulations to understand the outer solar system's dynamic behavior under this hypothetical planet's potential influence. These simulations suggest that a massive, distant planet could naturally produce the observed orbital configurations of trans-Neptunian objects. For instance, simulations predict that Planet 9 could maintain its orbit over the solar system's lifespan while shepherding TNOs into clustered orbits. This phenomenon, known as mean motion resonances, occurs when the gravitational pull of the planet and the TNOs synchronize over time. The quest to pinpoint Planet 9's location is guided by detailed analyses of orbital mechanics. These analyses consider factors such as the orbital period, inclination, and eccentricity of potential orbits for Planet 9. By comparing these theoretical orbits with the observed trajectories of TNOs, scientists can refine their predictions about the planet's whereabouts. The intrigue surrounding Planet 9 extends to its potential origin and the implications for planetary formation theories. If Planet 9 exists, it might have formed closer to the Sun before being ejected to its current distant orbit by gravitational interactions with other giant planets like Jupiter and Saturn, a common occurrence in the chaotic early days of the solar system. Alternatively, it could have been captured from another stellar system, which would make it an extraordinary example of planetary migration and capture dynamics. The Kuiper belt, a vast ring of icy bodies beyond Neptune's orbit, is a frontier of our solar system that continues to intrigue astronomers. Within this belt, a peculiar clustering of orbits among distant objects has been observed. These objects, known as Kuiper belt objects (KBOs), follow paths that seem to huddle together, particularly at their closest approach to the Sun, known as perihelion. This clustering is difficult to attribute to mere chance, considering the immense distances and the sparse distribution of material in the Kuiper belt. To unravel this celestial mystery, scientists have turned to dynamic computer simulations of the solar system. These simulations incorporate both the known planets and hypothetical ones, such as the proposed Planet 9. By inputting variables like the masses, initial positions, and velocities of these bodies, the simulations can calculate how their gravitational interactions might evolve over millions of years. Time and again, these models have consistently indicated that a planet with the characteristics attributed to Planet 9 could be the architect behind the unusual orbital patterns seen in these distant objects. The gravitational influence of a large, unseen planet could shepherd these KBOs into their observed alignments. This hypothetical Planet 9 is theorized to have a mass about 10 times that of Earth and an orbit that is significantly more distant from the Sun. The potential discovery of Planet 9 would not only solve the mystery of these orbital alignments, but also offer profound insights into the dynamics and evolution of our solar system. It would exemplify the power of gravity in shaping the architecture of planetary systems, and underscore the importance of computer modeling in modern astronomy. Insights from orbital anomalies and Monte Carlo magic to validate the intriguing orbital patterns of distant objects in the Kuiper belt and rule out the possibility of observational errors or random flukes. Researchers employ a robust statistical technique known as Monte Carlo simulations. This method utilizes random sampling to assess the probability of these orbital configurations occurring by chance. Through these simulations, scientists have reinforced the hypothesis that the peculiar alignment of these orbits is most likely a result of the gravitational influence of the proposed Planet 9. Monte Carlo simulations are particularly valuable in astronomy for their ability to model complex systems and account for uncertainties. By simulating a vast number of scenarios with varying initial conditions, researchers can derive a statistical distribution of outcomes. This helps in understanding the likelihood of certain orbital arrangements and supports the argument for Planet 9's existence based on its gravitational effects. Traditional methods of planetary discovery, such as direct imaging or transit observations, face significant challenges when it comes to detecting objects in the remote regions of the solar system. The extreme distance and faintness of these objects make direct observation difficult. Consequently, astronomers have turned to indirect methods of detection, which infer the presence of a planet based on the gravitational effects it exerts on other celestial bodies. These indirect methods include techniques like radial velocity measurements and transit photometry, which have been successful in discovering a multitude of exoplanets within our galaxy. However, for the distant and dim regions of our solar system, where direct imaging is not feasible, the gravitational perturbations observed in the orbits of Kuiper belt objects provide crucial clues. While the indirect approach has its skeptics, the consistency of findings from various independent studies adds weight to the argument for Planet 9. The continued use of Monte Carlo simulations, alongside other analytical methods, strengthens the case for this hypothetical planet and showcases the innovative techniques astronomers use to explore the frontiers of our solar system. The quest to understand the mysteries of our solar system has led astronomers to consider various explanations for the unusual orbital patterns observed beyond Neptune. One such explanation is the gravitational effects of multiple yet-to-be-discovered celestial bodies in the outer reaches of our solar system. These objects, potentially small and numerous, could exert a collective gravitational pull that influences the orbits of known trans-Neptunian objects. Another intriguing hypothesis suggests the presence of a distant, undetected star, sometimes referred to as Nemesis or Tycho, which could be subtly perturbing the paths of distant solar system objects. While no concrete evidence supports this theory, it remains a topic of scientific curiosity. These hypotheses fuel the ongoing debate and research in space science, a field characterized by its dynamic and evolving nature. Each discovery or observation adds a piece of the puzzle, enhancing our understanding not only of the potential Planet 9, but also of the broader mechanisms that shape planetary systems. The scientific method is at the core of these explorations. Hypotheses are rigorously tested against empirical observations, and theories are continuously refined. This iterative process is what allows our comprehension of the cosmos to grow. Pan-STARRS, one's groundbreaking search. A recent study titled A Pan-STARRS 1 Search for Planet 9 marks a significant advancement in the search for this hypothetical ninth planet. Utilizing data from the Pan-STARRS 1 survey, astronomers have made substantial progress in narrowing down the potential locations where Planet 9 might be found. One of the study's key findings is the elimination of 78% of the sky area previously considered possible hiding spots for Planet 9, based on earlier models and predictions. This was achieved by surveying with a completion depth of V21.5, which means the sky was observed to a visual magnitude of 21.5. At this depth, approximately half of the sky area could be confidently excluded as a location for a planet with the characteristics predicted for Planet 9. The choice of this particular depth for the survey is crucial. It represents a balance between the desire for thorough exploration and the practical constraints of telescope sensitivity and the finite amount of time available for such a survey. By focusing on this depth, researchers can efficiently allocate their resources while still conducting a comprehensive search. The implications of this research extend beyond the hunt for Planet 9. It also sheds light on the distribution of mass in the outer solar system and informs our models of solar system formation and evolution. The regions of interest, particularly those near the galactic plane, present significant observational challenges. The dense star fields and interstellar medium in these areas can obscure the faint signals from distant objects, making it difficult to spot something as elusive as a distant planet. Despite these challenges, astronomers remain undeterred, with 22% of the parameter space still unexplored. The focus now shifts to more refined and targeted observations. The Vera C. Rubin Observatory is set to play a crucial role in this endeavor. Its advanced optical capabilities and wide-field camera will enable astronomers to scan the remaining search areas with unprecedented effectiveness. The observatory's legacy, Survey of Space and Time (LSST), will conduct a decade-long sky survey, cataloging billions of objects and providing detailed data on regions where Planet 9 might be located. With its ability to detect faint objects over a vast area, the LSST is essential for spotting the subtle signals that could reveal this elusive planet. Theoretical advancements are equally crucial in directing the observational search for Planet 9, ensuring that efforts are aligned with the latest scientific insights. The collaboration, highlighted by data integration from Pan-STARRS 1 and contributions from the Vera C. Rubin Observatory, exemplifies the collaborative nature of modern astronomical research. Whether or not Planet 9 is discovered, these efforts significantly enhance our observational capabilities and deepen our understanding of the universe. They push the boundaries of space exploration and thoroughly explore the scientific, observational, and theoretical frameworks that drive the ongoing search for Planet 9. Do you believe in the existence of an unseen planet in our solar system? Share your thoughts in the comments below. If you're intrigued by space mysteries, hit that like button and subscribe for more fascinating updates.